In this section, in this chapter, we are discussing about separation axioms. There are various kind of separation axioms we have already told. For example, Hausdorff spaces, regular spaces, normal spaces. A space is called Hausdorff if any two different points can be strongly separated by disjoint open sets. A topological space is called regular if points and closed sets can be separated strongly by disjoint open sets. A topological space is called normal if any two disjoint closed sets can be separated strongly by disjoint open sets. We have also studied some properties of Hausdorff space, regular space, normal space. We have examined that Hausdorff property is hereditary, regularity property is hereditary. That means every subspace of Hausdorff space or regular space is Hausdorff and or regular respectively. We have also seen that Hausdorff property or regularity property are productive property. That means any collection of Hausdorff spaces, and if we take their product, then the product is also Hausdorff. If we take any collection of regular spaces and take their product, then the product also becomes regular. But what happens in case of normality? We shall see that normal spaces is not even finitely productive. Let us go to slide presentation. As I told, in this section, my main motivation is to show that product of normal spaces may not be normal. Even finite product of normal spaces may not be normal. We already know that RL, that is real number system with lower limit topology, is normal. We shall show that product of RL is not normal. We have already seen that product of RL, that is RL cross RL, is not Lindelof. We shall use similar kind of techniques in this proof also. Let us first prove that normality is a closed hereditary property. In the proof of RL cross RL, we shall show that RL cross RL has a closed subspace which is not normal. That will prove that RL cross RL is not normal. So, let us first prove that closed subspace of normal spaces is normal. Let X be a normal space and Y be a closed subspace of X. Then to prove that Y is also normal, we have to take two disjoint closed sets A and B in Y. Then there exist disjoint closed sets E and F in X such that their trace in Y are respectively A and B. Now, as X is normal, then E and F can be strongly separated by disjoint open sets in X. If we take the trace of these disjoint open sets in Y, then we can separate disjoint closed sets A and B in Y by disjoint open sets. This proves that closed subspace of normal spaces is normal. So, we are going to prove that product of normal spaces may not be normal. We shall show that RL, Cartesian product RL, is not normal. As we have already told that if we can prove that RL cross RL has a closed subspace which is not normal, then our work will be done, as we have already proved that closed subspace of normal spaces is normal. In a previous example, we have proved that the line L defined by x minus x such that x belongs to R is a closed subspace of RL2. In fact, if we can take a point outside this line, then we can get a basis element containing that point which misses the line, as is shown in the picture. Further, it can be shown that if we take a single point on the line L that is an isolated point, we can get a basis element of RL2 which meets the line L only at a single point, as is shown in the current picture. So, the subspace topology on L induced from RL cross RL has the discrete topology. Since the subspace topology on L induced from RL2 is discrete, then any subset A of L which is closed in L is also closed in RL cross RL, because L minus A is also closed in RL2, as L has the discrete topology. This means that for every non-empty proper subset A of L, one can find disjoint open sets UA and VA containing A and L minus A respectively in RL2. So, what we have done, that we have taken a closed set in L, then this set is also closed in RL2. Now, as A is closed in L and L has the discrete topology, so L minus A is also closed in L and hence closed in RL2. So, A and L minus A both are closed in RL2. Now, since we have considered RL2 as normal, therefore, we get disjoint open sets UA and VA containing A and L minus A respectively. Now, let us consider a set D whose points are rational. That means D is the set of all points x, y belongs to R cross R such that both x and y are rational. Then D is of course dense in RL cross RL. Now, we define a mapping F which assigns to each subset of the line L a subset of the set D in the following way. We define f of A is equal to D intersection A whenever A is a non-empty set and A is a proper subset of L. F of empty set is equal to empty set, f of L is equal to D. Note that f of A is non-empty because as D is dense in RL2, we have D intersection UA is non-empty because UA is an open set in RL2. We claim that F from the power set of L to the power set of D is injective. For this, let A be a proper non-empty subset of L. Then our definition says that F of A is equal to D intersection UA, which is neither empty as UA is open and D is dense in RL2, nor all of D, since D intersection VA is non-empty. So, to prove that F is injective, it remains to show that if B is another proper non-empty subset of L, then FA is not equal to FB. Since A not equal to B, one of the sets of A and B contains a point which is not contained in the other set. Suppose X be such a point. So, let us consider X belongs to A and X does not belongs to B. Since X does not belongs to B, it means that X belongs to L minus B. Therefore, we have X belongs to UA intersection VB. In fact, UA and VA gives the disjoint separation of A and L minus A, and UB and VB give the disjoint separation of B and L minus B. So, these points belongs to UA and not to UB. Therefore, D intersection UA is not equal to D intersection UB as we desired. Thus, F is injective. Next, as D is countable and L has the cardinality of the continuum, we have that cardinality of power set of D and cardinality of L is equal. That means there exists a bijective mapping, say phi, from power set of D to L. Now consider the composite mapping phi compose F from power set of L to L. Since F is injective and phi is bijective, therefore, phi compose F is an injective mapping from power set of L to L. This is a contradiction because we can't get a injective mapping from the power set of any set to that set. Next, we shall prove that every linearly ordered topological space is normal. We have already encountered an example of linearly ordered topological space which is normal. In fact, R with usual topology is a linearly ordered topological space which is normal. The topology of R is taken as basis as open intervals. Here also the technique is same, but some differences are there which will be handled with the proof of the following theorem. The theorem: every linearly ordered topological space is normal. Proof: let X be a linearly ordered topological space. We assert that every interval of the form x y, where x is open and y is closed, is open in capital X. In fact, if x has a largest element and y is that element, then x y is just a basis element about y. In case of R, this becomes the open ray, because in case of R there are no largest element. Now, if y is not the largest element of X, then the semi-open interval x y equals the open set x y bar, where y bar is the immediate successor of y. Now, let capital A and capital B be two disjoint closed sets in capital X, and assume for the moment that neither capital A nor capital B contains the smallest element, say A0 of capital X. Then for each A belongs to capital A, there exists a basis element about A disjoint from capital B. It contains some interval of the form x A, where x is open, A is closed. Here is where we use the fact that A is not the smallest element of X. Choose for each A belongs to capital A such an interval, say x subscript A, where x subscript A is open, A is closed, which is disjoint from B. Similarly, for each B belongs to capital B, choose an interval YB, where YB is open and B is closed, which is disjoint from A. Now, consider capital U is equal to union of open interval XAA, where A runs over capital A, and capital V is equal to union of intervals YBB, where B runs over capital B. Then capital U and capital V are open sets, as they are union of open sets and they contain capital A and capital B respectively. We claim that capital U and capital V are disjoint. So, suppose on the contrary that Z belongs to U intersection V, then Z belongs to the intersection of the intervals XAA intersection YBB for some A belongs to capital A and for some B belongs to capital B. Assume that without loss of generality A less than B, then if A less or equal to YB, the two intervals are disjoint, while if A greater than YB, we have A belongs to YBB, contrary to the fact that YBB is disjoint from A. A similar contradiction occurs if we take B less than A. So, we get disjoint open sets U and V containing A and B. Finally, assume that A and B are disjoint closed sets in X and capital A contains the smallest element A0 of X. Then the set singletoned A0 is both open and closed in capital X. By the result of the preceding paragraph, there exist disjoint open sets U and V containing the closed sets A minus singletoned A0 and B respectively. Then U intersection singleton set A0 and V are disjoint open sets containing A and B respectively. So, in case that if X has a smallest element, we also prove that if A and B are two disjoint closed sets, then there exist disjoint open sets U and V containing them respectively. Therefore, every linearly ordered topological space is normal. In the coming section, we shall see that linearly ordered topological spaces satisfy more stronger separation property called completely normal. We have proved that every linearly ordered topological space is normal. Next, we will discuss some facts about well ordered spaces, that means ordinal spaces. For this, first we require some prerequisites on ordinal numbers, which we will discuss in this section. Next, we discuss some facts about well ordered sets. One of the important property of the set of natural number is that if we take any subset of n, then it has a smallest element. This property leads us to the following definition. Let X be a non-empty set with a partial order relation less or equal to. Then that relation will be said to be a well ordered relation if under that relation every subset of capital X has a first element. Theorem: every non-empty finite ordered set has the ordered type of a section 1 to n of n. So, it is well ordered. That means that if we take any finite set, you can choose a relation, you can choose a order relation such that it can be identified with the initial segment 1 to n of capital N. So, this is a major theorem in mathematics called well ordering theorem. If A is a set, then there exists an order relation on A, that is a well ordered. That means every set can be well ordered. In fact, there does not exist any concrete proof of this theorem. So, this theorem is called rather than axiom. As a corollary of this theorem, we can say that there exists an uncountable well ordered set. Next, we state the following notation. Let capital X be an well ordered set and alpha be a member of capital X, then we shall denote by S subscript alpha equal to the set all beta belongs to capital X such that beta less than alpha. This set S alpha will be called a section of capital X by alpha or initial segment of X determined by alpha. Theorem: there exists a well ordered set capital A having a largest element omega such that the section S omega of A by omega is uncountable, but every other section of capital A is countable. In fact, if capital B be an uncountable well ordered set and capital S be the well ordered set 1 to Cartesian product B in the dictionary order, then some section of C is uncountable. Let omega be the smallest element of C for which the section of C by omega is uncountable. Then let capital A consists of the section along with the element omega. That will complete the proof of this theorem. Note that S omega is an uncountable well ordered set, every section of which is countable. Its order type is in fact uniquely determined by this condition. We shall denote the well ordered set A is equal to S omega union singleton omega by S omega plus 1. The most useful property of S omega for our purpose is expressed in the following theorem. So, we conclude this section with the following theorem. If A is a countable subset of S omega, then A has an upper bound in S omega. We will leave the proof of this theorem. With this, we end this module presentation, which will be required in our future work. Let us pass to next module.